first things first, thank you guys for coming. Good afternoon to you all. Today, the topic of the lecture is the code we've been developing for simulating scale resolving simulation of turbulent flows, namely SOD2D. So those are the main participants of SOD2D so far, or the main developers: myself, Lucas Gasparino, my boss, Dr. Oriol Nkul, our resident postdoc, Dr. Jordi Moela, and Mr. Felipe Ospiga from NVIDIA itself, which has been a huge contribution related to the OpenACC part of the code, and just generically being very supportive of us. There are more users and a few other developers here at BSC, but most of the work is carried out by us. So the motivation for this code is that in moving CFD towards the exascale, we are faced with many problems. So mostly, considering that we're dealing with scale resolving simulations, we have the problem of the computational cost. LES and DNS, or large eddy simulation and direct numerical simulation, are forms of numerical simulation of flows that require intensive meshing, as can be seen in the picture above. And there is also the problem that we try to resolve as many turbulent scales as possible, which means not only a fine mesh, but also small time steps. So we need a large quantity of time steps over a large mesh, which compounds rather quickly. And the mesh being shown here in particular is actually a linearized version of the meshes that we use. So there are actually quite fewer elements, but wherever lines cross, there is actually a node. So meshes with a few 100,000 elements end up with quite a few million degrees of freedom. That's the direction that we're trying to move in. And apart from this complexity associated with the physics, with the numerics, because of course the numerics for computing something like the turbulence displayed here in figure 2 are actually quite expensive in itself. So it demands new algorithms. We also have the problem of parallel efficiency, because of course we would like to run these on supercomputer clusters distributed over many nodes, and this leads to a lot of parallel efficiency problems, which we would like to try our hand at. Speaking of SOD2D itself, the old joke that the acronym comes first, and then we think a name on it. So originally, this was a very small test code for some of the proposals of my PhD. And after some hackathon with Felipe Ospiga, this grew way out of proportion, to the point where now we have a spectral high-order code to solve partial differential equations, meaning it's a code in Fortran, so old style, old school Fortran 90, coupled with OpenACC for the GPU porting, and MPI, Fortran MPI routines for the parallelization over multi-processing elements, meaning we can either run full CPU parallel mode, or we can run a hybrid of full CPU for the coarse grain parallelization with GPUs on the fine grain parallelization. So we are using CUDA or MPI in this case. The spatial discretization method, as implied by the name, is the spectral element method, which is a subset, is a tentative optimization on the finite elements method, which we'll get into more details. And this code has been taught to deal with fully unstructured meshes composed of p-order hexahedron. It's fully open source and available at the address displayed below with an MIT license. So, getting a little bit into what the SIM method is, what the spectral method is, essentially we're taking Lagrange type elements where their shape functions can be decomposed in a triple product in the case of hexahedron, and we are trying to use this to our advantage. So as in the picture to our side, this is not exactly what a spectral element is. This is just a Lagrangian element but it gives an idea of what I'm talking about, where a shape function of a node is the product of two Lagrangian polynomials at that node. So a node can be decomposed in its I, j, and in 3D, k components. What this leads to us is that those p-order hexahedron are very easy to formulate. We have, it's very easy to construct the Lagrangian shape functions for them and their derivatives. And in the case of GLL positions for the nodes, we have functions to compute those positions and weights at these nodes. So they're not particularly cumbersome. We don't have to hard code anything. There is, as we'll be seeing shortly, a massive reduction on the arithmetic complexity of this algorithm, because we will be able to eliminate a lot of operations compared to classical finite elements. And because the nodes are not equispaced, because they have this Gauss-Lobato-Lagrange, Gauss-Lobato-Lagrange distribution, they are not prone to spurious oscillations. So you will not see sudden spikes in the shape functions way greater than 1 outside of the nodes, which would lead to essentially spurious oscillation in the solution. The GLL element is basically immune to that. The disadvantages is that spectral methods are prone to what we call aliasing effects on the convective operator. So without certain special treatments, you will still see spurious oscillations due to insufficient integration, which can be solved rather easily. And perhaps the biggest problem right now is that generating a full hexa p-order mesh is a rather tall order. Right now, how we deal with this is by using either Gmesh or ANSA, which have certain higher order full hexa capabilities. And as shown in the slide before, we end up with meshes similar to these, where the elements are a bit ugly, but because of the way our code is built, it can handle this, let's say, ugly discretization. So coming to what's actually the meat of SOD2D, which are the operators in the Navier-Stokes equations. Here I'm presenting a very simplistic discretization based on an actual convection diffusion model for a scalar, which later can be extended to the more complex Navier-Stokes case without loss of generality. So bearing with me on the notation here a bit, I know it's a lot of symbols and indexes. In essence, we need to construct a mass matrix related to our temporal term, to our partial temporal derivative. We have to construct residuals for the divergence of the flux and for the Laplacian terms as well, or the convection diffusion terms. Now, those are based on standard finite element operations. There is no magic here whatsoever. What happens is that on the mass matrix operator and on the divergence operator, what happens is that the GLL quadrature, where we put essentially what we are doing is coinciding the quadrature node with the element node. What happens is that the shape functions evaluated there are essentially 1 or 0. We observe that before implementing. So what we actually implement are operations that already take this into account. So for example, on the divergence of F, where instead of having a sum over all of the Gauss points for every node of the element, we essentially just fill each node. Remembering that an element of a hexahedron of order P8, for example, can have an order of 729 nodes and 729 Gauss points, yeah, this is actually rather essential for us. And another interesting advantage is that the mass matrix is not, ends up being naturally diagonal. We don't have to do any special tricks with this mass matrix. It ends up being lumped naturally. And moreover, with the GLL distribution that we employ and the Lagrangian shape functions, we end up with positive definite diagonal mass matrices, which are essential for what we are trying to do. So for example, what this means is that there are no negative entries in any terms of the elemental mass matrix. Those elemental operations, once they are carried out, they are combined into an assembly. So we assemble local elements into a global array or global mass matrix and global residuals for the convection and diffusion operators. And in case we have a mesh partition over multiple CPUs, multiple GPUs, we use point communication between the arrays using very simple MPI send receive routines to ensure that each partition knows the information that it has to be communicated prior to following up with either a runge-kutta step or with some form of an implicit method that we can also implement. Now, this is why we implement this as a hex-based. Now, the same method can be applied to any kind of element, so it doesn't matter if it's a tetrahedra, a hexahedra, or even a prisma. We could actually derive this, but what we notice is that with the hexahedra, we can also employ a lot of operation reductions to those gradients of the shape function. So you will notice on the right-hand side here that each one of these variable gradients, especially the shape function gradients, instead of looping over each node of the element per Gauss point, they are only looping over the ij and k indexes. So remembering the figure of the Lagrangian element with the ijk indexes, this is what I'm talking about. And these loops, they are of order p order. So again, remembering the P8 with 729 nodes, instead of doing 3 loops with 729 entries, we do 3 loops with 9 entries for a P8 element, which is already considered a bit expensive for us. But over P4 elements, this is incredibly quick. It does create a bit of complexity when implementing, but this is all handled within the GPU parallel loops. So in terms of OpenACC implementation, this does not bring extra complexity apart from setting up appropriate memory. Now, finally, regarding the issue that I mentioned on the aliasing terms, when we get to the Navier-Stokes equation, following this paper of Kennedy and Gruber, we discovered that we can actually implement these skew-symmetric expansions to the convective terms of the Navier-Stokes and end up with a formulation that is actually anti-aliasing. So in other words, we do not need to scale the P order up to more than 8 just to compensate for aliasing. We are actually able to run with P3 and P4 elements without spurious oscillations on the flow fields, which helps diminish the elemental computations quite a bit. Now, the part that actually everybody is interested, the GPU implementation. It's a very basic implementation. The strategy is that since each element has a massive number of nodes, a massive number of Gauss points, what we do is associate one thread block of the grid with one element, and then each thread in this 1D thread block is responsible for computing one of the Gauss points of the element, meaning any other operations, the dimensional loops and the loops over the ijk indexes are carried sequentially per thread. This introduces to us a 2-level parallelism, which we've noticed that is actually quite a bit better than trying to group elements into a thread block and requiring that each thread in a thread block handles one element. For orders greater than 2, this is actually a lot more efficient. And of course, as mentioned before, this strategy is easy to combine with multi-GPU implementations, because once the assembly of the convective and diffusive residuals is carried out for each partition, we just need to ensure proper communications at the halo nodes. on an RK method, explicit RK4 advancement, for example. This requires one communication per substep of the Runge-Kutta, which is actually quite cheap. This is a skeleton of a loop that we implement. I can't put the full code here, unfortunately, because it ends up being quite a big implementation. But this is a very generic loop that is implemented in SOD2D. And the interesting parts here are exactly the mirror of what I just said. The ILM loop, which is just the elemental loop, is carried out on the OpenACC gang directive, or essentially associating with the thread block. And the Gauss point loop is carried out on an inner ACC loop vector, meaning that we are associating a thread, or more specifically a warp, but I don't want to get into details of this, but essentially each thread of the thread block is computing a Gauss point of the element. Then we have any other sequential operation that we might have, like, for example, the gradients of the shape functions, the multiplication with the inverse Jacobians, finally leading to the assembly, which is also carried by threads, because in this scenario, nodes and Gauss points are coincident, so we can use them interchangeably. And finally, if multi-GPU is involved, we call them PI routine appropriately. But this is very generic and is what we use for both convective, diffusive operators, as well as just any other generic operator that we have to do that mimics this skeleton function. Of course, just distributing the mesh into the grid for the GPU is not enough. We need to handle memory. And one nice thing that we did with SOD2D is that all the GPU memory is filled at the beginning of the code. So during the meet operation, so when we are running the time steps of SOD2D, there are no host device transfers unless we are doing output, in which case there's only device to host transfer operations. Essentially, this means that we are reusing information that's already on global memory of the GPU, which, as we all know, tends to be quite a problem for GPU codes. And we decided to handle it by simply not having it. And the other important part is how we handle the memory hierarchy of the GPU. So we know that a thread block can have shared memory and registers per thread. And if we go back to our gang and vector loops, what we actually do is that we declare certain local variables gathered inside these loops as private to each one. So for example, instead of always accessing the global variable containing velocities, for example, we actually create a block of contiguous shared memory for the velocity and access that as private memory. And as well, the gradients of the shape, the isoparametric gradients at the Gauss point are associated as private to the thread, which implies that they are located on the local memory or the register of the thread, if possible. This not only guarantees safe access, so there is no chance of a block accessing information that does not belong there, but it also implies that we are using a lot of the GPU caches, which grants quite a bit of speed up for us. Now, after all of this, what do we get out of it? So we've been running SOD2D for a while now. The code is around, so a serious implementation of SOD2D is around about a year now, being carried by us. And we've tested this on multiple architectures now. So here at BSC, we have a Power 9 architecture composed of V100 GPUs. As well, we had access to A100 and even Age Hopper 100 GPUs, so that we could do these speed-up testings, as well RTX 3080 and an RTX 3090, which we consider as interesting platforms for testing, because we hope that one day LES can become industry standard. so that engineers with a workstation, with a relatively cheap workstation, can compute their models on desk without requiring a supercomputer. And just for reference here, we have a time per time step obtained in Mare Nostrum with this with what we call the 85 cube mesh. This is a mesh that has around 60 million nodes, and we were seeing an average of 1.7 seconds per time step. So when we look at the same thing for the H100, what we are dealing with is a time step being carried in 0.12, a bit more than 0.12 seconds. So one GPU presented a 10 times speed up over a full node of Mare Nostrum. Remember that this run on Mare Nostrum is fully parallel. It's run on the 48 cores of the node. We didn't want to do this across nodes to avoid any possible communication problems between nodes. So this testing is right now very simplistic, but we did do scalabilities after. And what we were seeing is something around this on Polaris. So a few months ago, we did a hackathon on the Argonne Polaris machine, where we tested meshes of up to 2 billion nodes using up to 400 A100 GPUs, the DGX versions of these GPUs, of course. And the times per DOF that we are seeing are actually quite fantastic. We are very happy with these timings. So we did, of course, measures other things such as the time it takes for MPI to run, memory transfers that are occurring. And what we see is that we have no memory transfer whatsoever. And the MPI part, even at 400 GPUs, was not that important compared to the time taken by the two kernels, the convective and diffusive. I must note that both of these experiments, both the single GPU and multi-GPU experiments, were conducted with single precision numbers. We do have the capability of running with double precision numbers, of course. We can switch between the two of them. But for GPUs, we usually decide to run with FP32, mainly because we want, again, to be able to run on multiple architectures, not necessarily just the ones capable of good performance in the low precision. So again, an RTX 3080 or a RTX 5000, for example, which are GPUs that mainly work with single precision. Just to provide some conclusions, I think the picture explains it quite well. What we were seeing with GPUs is a rather unlimited power situation, or more specifically, unlimited possibilities. We can scale very well with GPUs. Modern GPUs, such as the H100, are providing big gains over already established hardware, such as the A100. We saw on kernels, for example, we saw speedups of 2 times from the H100 over the A100, which for both me and Filippo was actually a bit scary, and we are quite happy about that. We are doing a lot to improve on SOD. So, for example, now we can select between managed memory and non-managed memory. We have full explicit memory transfers. We don't rely on managed memory anymore. We are exploring possibilities of implicit solvers for the compressible as well, which have their own challenges. And just a few weeks ago, we coded an incompressible version of SOD2D using a good and old fractional step method. And we're on the phase of testing that. But right now, the numbers are quite satisfactory. Thank you very much for your attention, and I'll be happy to answer any questions.